So here we are. I want to talk about what's almost, it's more like a research project than anything practical, but it's kind of works. And it's a tool called Include What You Use that I hope to demo to you tonight a little bit. But mostly I want to talk about how it works and why it works the way it does, because it's not as simple as you would first think. So it's colloquially called IWYU, which is incredibly hard to pronounce. So we usually just say include what you use. But it's kind of a word. People talk about IWYU friendly, etc. And I don't know, are people familiar with the concept of include what you use? I'm glad, because I have millions of slides on it, so prepare. So include what you use are essentially two things. It's a principle for optimizing your include dependencies, targeting a few goals that I'll mention later, and it's also a tool to fulfill that principle. And the principle is really simple superficially. It says that if you use a symbol, you should include the header that defines that symbol. End of story. So why is this interesting? Well, it turns out that one of the biggest costs of, or one of the biggest compile time costs includes in a lot of ways. Measurements I've done show that the larger your translation unit is, the longer it takes to compile. Surprise, surprise. But there's also the cost of statting include files repeatedly to find out if they've changed or not. So there's a measurable cost to every include statement anywhere, or every include directive. And to reduce that, we simply reduce the number of includes. But there's also the dependency tangle that happens when you have lots of include files. If we have, say, 200 includes of a single header and we change that header a lot, we'll have to recompile everything that includes it. So we want to minimize the number of includes we have to the bare minimum. Otherwise we'll be paying in recompiles every single time we change anything. And this is also one of the can't find the word. This is one way of cutting dependencies, or one of the motivations for cutting dependencies. Because we want to make sure that, we want to make sure that an unrelated change doesn't cause us to recompile something that didn't expect to recompile. So it's sort of there's sort of a soft dependency, and we'll see examples of this later. I don't want to lose myself already. And by cutting dependencies, we encourage refactoring. We can change internal details of a header without affecting things including it, unless we absolutely have to. And I think now would be a good time to start showing examples, I guess. So given this code, show of hands, should we include value.h in aggregate.h? Yes or no? Or yes, rather. Show of hands. Okay. Why or why not? Because aggregate will be it will be useless without this include, because we can't know the size of aggregate, so we can't really use it if that include is not present. So here, pretty much the same thing. Those are the plain basics. Do we want to include value.h? Probably not, because we're storing a pointer, so we can get away with a forward declaration. And we want to reduce the number of includes, so we want to get rid of it. Clump.cpp, well, clump.h, we need it, because otherwise this declarator isn't available. Value.h, well, since we're calling methods on it, yes, we need it. If we were just storing the pointers, we wouldn't need it. So it's sort of a, we don't really know. Or in this case, we do know because we're calling methods. The compiler wouldn't compile without that include. So here's another simple one. Do we need this when we print value.h? Not really. It's a reference, so the compiler doesn't need to know its size, and it can just it can compile even without it. Do we want it? Maybe. It depends. Depends on if we see this function as part of this class or not. If we see this function as providing this class, we probably don't, because it's a print thing. It's probably a leaf somewhere down here. If we call it, we probably already have a value somewhere that we want to pass through it. And the examples, I mean, the simple ones are simple, but it gets pretty hairy pretty soon. If we have a getVector method somewhere, function that returns a vector. Even though it's not written in the source code, we're actually using the vector here. We're calling its empty method. So we probably need the vector somehow. IOStream is a given. We need it to be able to call the cout streaming operator. And this is where it gets hairy. Things like type defs. Do they actually require this source type to be defined? Turns out they don't. The compiler doesn't really care as long as you provide it somewhere where you start using it. So this include is not strictly necessary, but think about what would happen here if we didn't put it in there. Then we'd have to include string t and string, which would sort of defeat the purpose. The type def is no longer useful because we have to know what it means anyway. So we probably want this string in place. And then things like the return value. Does that require the type to be defined? Not really, but in order to be useful, yes. The const reference argument, does it require the type to be defined in order to declare it? Nope. We can just forward declare everything here and have it compile, so we don't need to include string t and we don't need to include string. But is it useful? What would we do here without that type? We can't really use the toLower function in any meaningful way without it having provide the string t type. Every single call we make to it will need that type available. Okay, sure.
On your previous slide, is this guiding principle here that you don't want to force anyone to know your includes? Or if you include string t, then the guiding principle is that you could not require anyone to find out.
Exactly. Yep. Well, for the most part, I think that's what turns out to be a really weird consequence of this analysis. That it sort of depends. Sometimes it's obvious. Sometimes it's really weird and hard to reason about, especially with templates. And I think I have a template example later that I can't even explain. But you have some sort of intuitive feel for what would be right, but I can't explain the mechanics. And this is actually a really good one. Who provides operator for string t? That could be defined somewhere else, and we don't really know at this point what code is using what. So It's not clear cut exactly. And this is another funny one. Nothing weird here. This seems wrong, but it's actually okay, because the argument list doesn't need to... You can pass a thing by value without knowing its complete type. But this has an implicit conversion as well. So what happens here? Do we want to... This becomes necessary here, even though we're not using that type. But do we want to force that on the callers to do magic? Probably not. So we want to pull that back, because there's an implicit conversion from int to magic int, etc., etc. So it turns out to be a really hard problem to reason about. And this is one of the reasons we love C++ so much, because there are a million ways of doing the same thing. And we run into things like this. It happens all the time. And if you think this looks weird, then think about precompiled headers. It's exactly the same thing. And people tend to use them without thinking much. And this is one of my favorites. This came up on a mailing list recently. So we have a constant nested in a struct that we use inside inline assembly. And that's perfectly valid C++, and there's no reason we shouldn't include some type here, even though that will be really hard to discover from the structure of the language, because it's in another language. So when I talk to people about this, because this gives me tremendous anguish, I hate this stuff. And what they always say is, oh, ho, 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 this is such a simple problem. Just ho, 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 Perl scripting batch files, la, 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 la. Unfortunately, it's not just a minimization problem, but because what happens if we boil down includes to the bare minimum is that we lose all the dependency cutting benefits. If we just remove everything that's not necessary, we can't pull out a CPP file, or rather a header file, and use it somewhere else, because it will have a hell of a load of implicit dependencies from its bare minimum of includes. So it's sort of a trade-off where we want to push up things that we depend on, but we want to remove things that we absolutely don't depend on. So include what you use as a tool tries to figure out first what the compiler requires, which is kind of the easy problem, but also what the author intended, which is usually the really hard problem, because that author is a person and they don't tend to be very structured. And we can't solve this with Perl. I'm sorry. So I turned to the Clang project, and you mentioned LLVM. This is the C++ compiler on top of the LLVM project. I don't know how many people have not heard about it. Everybody has heard about it. That's good. So besides being a really good compiler, it's also sort of a compiler as a library, which is really nice. They encourage tool building on top of it. And it comes, you can pull it out, build it, and link to its libraries and use its internal headers, etc., to your heart's content, as long as you're prepared that it moves really quickly. So relying on private details tends to be painful. And the public API is really, really thin, so you can't really do anything useful with it. But it tends to move in a nice direction, though. They generally don't remove useful things. So include what you use listens in on one secret channel to collect the entire include graph, all preprocessor definitions, and their uses. macro uses most significantly, or defined constants, etc. And then there's another pass that parses the actual language, and we can listen in and collect definition points and uses of all symbols, of all C++ symbols in the program. And then we have two huge, wonderful sets that we can start cross-referencing. Because now we know where everything is defined and where everything is used, and we can start reducing until we reach some sort of optimum. Yep. And the preprocessor, there's a preprocessor callback library that's fed from the Clang preprocessor, where we get all the information about if-defs, macro calls, macro definitions, includes, you name it. The recursive AST visitor is the other half. That's the part that once the C++ program is parsed, we can traverse the AST to find everything that's used and defined in some sort of order, and pull out information. And the intended use case is essentially this. We won't include what you use to be a compiler replacement. So whenever you make your project, you substitute your compiler for include what you use, and the build system provides all the the compiler arguments, so that your code builds just as it would have if you built it with Clang proper or any other compiler. And which means you have include paths at hand, you have command line include defines, etc., 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 language standard overrides, etc. So we can be really nimble in what we accept because we have all the data. So you can use it either like this or like this in a sane development environment. It doesn't really work with Visual Studio, unfortunately. So I think it's kind of obvious why this is difficult, but there are some things that once you've gotten over the basic hurdles, this turns out to be even more difficult. Okay.
So how do you, if your project isn't written for Clang, if it's basically not used, let's say, or I have to make it compile with Clang and translate my project into Clang to compile with Clang first and use a makefile to do it.
Pretty much. I I made it my life's goal to port this to Windows when I joined the project, and it hasn't really worked out very well. But I usually run it standalone, and I'll show you in a demo later, on Windows. And there are some things that it chokes on from the Microsoft headers, for example. But the Clang project is pretty adamant about getting full getting full Microsoft support. So they simulate the compiler, and they try to accept as far as possible the SDK headers and the STL headers. So we're sort of getting there for free as Clang is maturing.
That might be the biggest challenge.
Yeah, I think so too. And then the remaining challenge is to sort of extract the build information out from Visual Studio and transform it into something that Clang understands. But that's also something that Clang is working on. They have a Clang CL front end, a separate front end or a driver, I suppose, that accepts the Visual Studio command line arguments and translates them into internal sane form. So I think one of the biggest, well, one of the challenges anyway is understanding all these uses. What's a use and what's a full use, what's a forward declare use, and what's not a use at all. And we run into things like covariant return types. They happen to where a return type can be omitted. If you use a covariant return type, you have to include the type for some reason, mandated by the C++ standard. So we need to sort of take that into account when we process everything to make sure that we understand how everything works. And author intent by far is the hardest. What does it mean when a template argument is used as a parameter to see out? Is that who's responsible for that, the author or the user, or both, or neither? It's really hard to tell sometimes. And we have a few really clear-cut cases that are really easy to tell, but where we can't really figure out how to convince IWYU to do the right thing, because it's so hard to see through the AST for the most part. And my absolute least favorite problem is the issue of private and public includes. And I think the simplest example would be this. If we hash include string to use our string, that's not actually the definition point of stud string. It's defined in bits basic string for GCC or X string for Visual Studio. And we need to know that stud string should come from string and nothing else. And so we need to sort of back out the include graph and find the right header and substitute that instead. And this is tricky. And it's especially tricky since it varies between platforms. So we haven't even begun looking at libc++, the Clang or Apple standard library, where they probably have some other convention that nobody understands. So we use heuristics in some places to try and parse the header to look for notes that this don't include this should be included instead, and jump there and pull things out of our behind. But it's working so-so. So this, and I might as well cover this. Started as a Google 20% project by the Google CTO. And they have a really hard policy for their development environment, which is a nice thing for them. But it means that include what you use is pretty much tied to GCC 4.2.1, plus some fixes I've made to make it sort of a balancing act on Windows. But there are mechanisms in place to make it, to port it to work on other platforms, but there's some work to be done there. And this isn't just a problem for the standard library. Things like Boost, you can imagine the include tangle to find out that yes is not in Boost MPL detail, blah 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 internal, but in fact it should include Boost MPL.h. That's something you will have to sort of build up underway. And then platform differences. Not only the sort of private public include is by far the biggest problem, but there are issues with the Microsoft compiler parsing things in a different way than the Unix side or the Apple side. And for some reason, Clang on Windows uses C++11 by default, whereas C++03 is by default on the other platforms, because Microsoft Visual C++ is sort of C++11 aware. So it's a kind of we're in a funny place. So my personal ambition is to move away from Microsoft and onto BSD or some other stable platform where I can develop this in peace. On GCC 4.2.1, probably. So, can I tempt you with a demo? No surprises. Our print function, which, since it takes a const reference, should be fine with a forward declaration. No surprises there either. And then we include print, we include value, and then the implementation details. I'm not sure why I stood. Oh yeah, it's there. It's so that it can be removed. So if I think we should be fine with print.cpp. So this is sort of the typical output from include what you use, where you feed it a CPP file or a translation unit. You can feed it source files, but it's hard for it to reason about the impact because it's very local. So it does a better job if it works on CPP files. So it argues that print.h has correct includes and forward declarations over here. Print.cpp should add these lines, nothing, and should remove these lines, studio.h, because it's not used. And the total would be print iostream and value.h. So if we might want to do something like this. Where we move that header to or that include to the header file. My gut feeling tells me that this should force include what you use to say that, hey, you should move that one. Replace that with a forward declaration and move it to the CPP file. So, and I think I'll be disappointed. Yep, because it's happy with this as well, because print.h and print.cpp are considered a component. So they're treated as one big thing. So if print.h would have been named flobber.h instead, it would have suggested to move the include. So it sort of sees things as it's a CPP file and its associated header as a big thing, and everything else as prone targets, and then it cleans out. You look concerned, Joachim.
Yeah, I think for this, for instance, I think it would make sense if print is a component I use, and I will always feed it value. I think that's where you run into problems. But if you have that, I would just like to include print.h, because the times I would do that and not feed value would be so seldom that it's more of a nuisance to me to be able to know exactly what types I might be using.
Yep.
Kind of take away some of the abstraction of the print.
Might actually be interesting to do this. If we, where are we? If we save this as, yes, and go back. It'd be interesting to see what the verdict is. Oh, okay. Now it starts removing print.h because it's defining its own print function and it doesn't care about print.h anymore. So we need to use it some other way. I'm not sure if that's what you expected, but well, it's not really.
I'm kind of afraid of that.
Yeah.
If you look at your CPP file.
Yeah. No, I see what you mean. It makes.
Where we use.
Yeah. This is the use, and this is the header we're sort of processing.
I guess we're hinting at a convention for defining what is a component.
Yep.
For some reason that what you use can understand.
Yep. And it's all heuristics. It's just they're named the same. But there are things we can do. Things like we can put pragmas on includes to say that always keep this one or re-export this include to clients, etc. for places where it gets funny. But I'm not sure. I don't really want to litter my source code with that kind of information. But it's until we figure the things out, I think that makes sense. So let's see. I'm not sure. I have a few more. Yes. Does anybody know how to kill all buffers? Oh, not sure what that. Let's see. Let's go to number. Oh, bugger. No, I lost them. dev. Number 2. So this is our type. A type def of this type to produce an alias. And then somewhere our main function that uses the alias. And this is one of the places where we want to analyze author intent, where we want to look at, look at this one and see that, hey, the whole purpose of this header is to re-export type under a different name. And I think that, let's see, include what you use, main. So here, include what you use thinks that this is the right thing to do. This weird construction, which is essentially wrong. But that in turn is because a type def, or rather a forward declaration before a type def in the same file is a signal that the user doesn't want to include this, or doesn't want to re-export the type that's being aliased. So by removing the type def, I think we should see that. Oh, okay, so now it's unknown. So if we include type.h and remove it from there, it's now also correct. I can't even imagine how to make it fail at this point in a meaningful way.
I think the failure case would be like,
oh yeah.
It's just included if you wouldn't have to use that. You could, that would work, but it's unnecessary because
Yeah.
the alias contains, that's a component that
So this,
does something else with re-export.
right. So this, exactly. So this would complain that main should remove type. It only needs alias. And boy, this is fun. So I actually have a third demo, and I'm not sure if you're up for it. We'll see. I figured this might make an interesting demo to see how how to sort of include what you use into working with this thing, because I think I figured out how to do it. So we can do some live hacking and see how it works out. Because this is a really horrible construct from a static analysis viewpoint, because it involves 3 different languages in ways that are not recommended. So direct, this is sort of a proxy file that only delegates immediately to indirect. which in turn defines this class, and we're using this static int. So given this code, we'd want this to be replaced by indirect, because we don't have any use for the middleman. So this will be out of context, but this is what I planned on typing hadn't it worked immediately. Right. So the recursive AST visitor in Clang has 3 phases, more or less. It traverses statements, declarations, and types by specific subtype. So there's a traverse for statement, there's a traverse declaration, there's a traverse function declaration, there's a traverse call expression, there's a traverse anything you can think of in C++. And it turns out there's a traverse Microsoft inline assembly statement that's not implemented in the base implementation of the recursive AST visitor. So all I had to do was to implement it, loop over all its expressions, of which the access of, let's see, this is more or less the only expression in that inline assembly. Everything else is garbage, according to Clang. So I loop over those and traverse them, and then all of a sudden it's all C++ again. I can get any call expressions in there, any member accesses, etc. So it's relatively simple once you find a case that it doesn't handle to actually make it do something, because we hook it up in traversal, and then there is code somewhere to handle, to determine whether it's actually a use or not already, except for some cases which are really hard. Eight o'clock. I'm a busy man. You are not. Patches welcome. It's actually a really, really interesting project, I think, but it's also really, really hard and tedious.